Thank you for the introduction and for the invitation of presenting my work, which is collaborative work between me, Gregory Leinders from SCK-SEN in Belgium, which is preparing the samples, and Kristina Kwasnina at the SRF for the experimental part using higher energy resolution fluorescence detected X-ray absorption spectroscopy. And today we will discuss about how to measure electronic structure of uranium in different compounds using multi-HERFD-XAS studies. My talk of today's will be divided in 3 parts with 2 poses. I will start with giving you insight why studying this type of materials containing uranium-5 and why HERFD-XAS is a key tool in order to study the electronic structure of uranium. And then I will focus on one of the compounds with this we have studied so far, showing results we obtain at uranium L1H, L3H, and M4H. And after that, I will go a little bit beyond X-ray absorption spectroscopy, using the calculations we have made in order to understand what the XAS was showing us. And we'll give you some a teasing slide about what's next on these studies. So first, why studying compounds like uranium oxide? Well, uranium is a very intriguing element because it's a very heavy element which has an electronic configuration containing S, D, and F electrons, and it has very versatile physico-chemical properties, and we can see it usually in solids in 2 different oxidation states, 4+, 5+, and 6+. And all of these electronic structure shows, well, it can be used for several applications, and the most obvious is, of course, nuclear applications. But from the fundamental point of view, the 5F electrons of uranium are behaving very differently if you compare the F electrons to the lanthanide series, just on top in the periodic table. And these electrons shows localization duality. That means that you can have them at the same time localized and delocalized, because they're hybridized with bands near the Fermi level. And so they are radially dispersed, but they can participate to the condition band while remaining localized depending on the compounds you are looking at. So they show a very different behavior, and this allows a very complex bonding character, being a mixture between covalency and ionic character. Of course, uranium is at the heart of nuclear applications, and there is a large amount of crystallographic data, physical, chemical, thermodynamic, lots of data because it has been studied for well, more than 50 years, sorry. But it is still not fully understood, and essentially because it's difficult to study, both experimentally and theoretically. On one side, well, uranium is radioactive, so you need specific laboratories and synchrotron facilities in order to have the opportunity to bring some radioactive samples there and measure them. And from the electronic and structural point of view of uranium, it is complicated theoretically, because crystal field, spin-orbit coupling, and electron-electron interaction in the uranium orbitals have similar magnitudes. So when you want to study theoretically such element, well, it's very expensive in terms of calculations power, and very difficult to study this way. That's why we need more and more data in order to develop more accurate calculations and understand better why it has such properties, especially the 5F electrons behavior. And well, the best way is to start having some compounds which have simplest behavior, And one option is to study 5+ uranium compounds, because they have only one 5f electron, and so at least in the F shell, you are removing the electron-electron interaction, and you have only 2 of the components in the calculations, which makes your life very easier when dealing with such compounds. Okay, and what compounds to study then? If you just consider simple oxides, which goes from uranium dioxide to uranium trioxides, actually you can found among the stable ones U409, U307, which are a mixture of uranium 4 and 5+. So they are mixtures, so it's not what we are looking for. Uranium 308 is a mixture of 5+ and 6+, so it's again not the best option for us. There should be uranium 205, which should be pure uranium 5, but it only exists under very specific conditions, so it's hard to obtain. And as far as I know, it has been obtained only on the Institute XPS experiment very recently. And here you have some example of the mixture discovery by Kvashnina and co-workers in 2017, where they used high resolution XAS at uranium M4 in order to distinguish what are the mixtures of these uranium oxide compounds. Well, so pure oxides is not possible for this study, so we looked at trinary systems, and often trinary systems in the forms of metal, uranium, oxygen 3 is a pure uranium 5. So we focused on this for the latest studies we made. What are the compounds? And here you have the crystal structure of those 3 compounds, so potassium uranate, sodium uranate, and rubidium uranate. At the first glance, you can see that potassium and rubidium uranate have almost the same structure, where there is a cubic structure of uranium around the metal of potassium or rubidium, and then each uranium is surrounded by an octahedra of oxygen in a regular pattern, so they are looking like perovskite type. However, for when you replace potassium by sodium, then you have distortion on the arrangement of the octahedra, keeping still an octahedra-like environment. Looking into details, rubidium and potassium uranates crystallize in the same structure and the same space group, and they are perovskite, cubic perovskite, and prototypical essentially. So in potassium uranate, there's no local disorder, and uranium is surrounded by 6 oxygen situated at 2.114 angstrom, and it's a very irregular octahedra. It's the same for rubidium uranate, where you have a regular octahedra, but the bond length is a little bit longer. So you can study them and compare them in order to have information on the impact on the structure of the bond lengths with oxygen, for example. The case of sodium uranate is a little bit more tricky because, as you saw on the previous slide, the octahedra are tilted in the structure, and there is also local disorder in the octahedra with 2 bonds getting closer while 2 others getting larger distances. So you have a spread out of oxygen 2x2 around the octahedra, and even the angle are changing with some distortion in the angle by almost 1 degree. So as a starting point, the best options for study 5F1 type of electronic structure of uranium is to go for potassium or rubidium uranate. And actually, I will focus today on the potassium uranate, for which we may expect crystal field splitting and spin-orbit coupling effects in the structure, while the same may happen on the rubidium uranate. But for sodium uranate, you will have a broken crystal field splitting, so it's a good way in order to see the spin-orbit coupling in more details, actually. Okay, how to study this? You have issues when you are studying uranium, essentially because if you look at the XANES, which is probing directly the electronic structure somehow, all the features are heavily broadened by the large cohort lifetime we have on uranium. If you look at the uranium L1H, it's typically over 17 EV. So then we will see almost no features. At the L3H, it's a little bit better, but you have already 8 EV broadening. So this is quite a lot. And here you have an example of some studies we made in the past of different compounds. And you can see that all these features are evenly broadened. So some of the white line here at the L3H are very broadened, but you cannot distinguish the different peaks which are making this broadening. And at the M4H, M5H, the broadening is even 3 EV, and that's why in the past, before the advance of high resolution, L1H and M4H were almost never used because well, you were not able to see anything out of these XANES results. Essentially because the expected crystal field magnitude is all of the time below 8 EV in the uranium compounds, and even the chemical shift, if you want to use XANES in order to follow the change in the oxidation states of uranium, when you move from 4+ to 6+, the chemical shift observed is always below 2 electron volts. So typically you cannot distinguish easily then. But if you use emission spectrometer and essentially Johan spectrometer in a Roland circle, here you have a schematic with the Roland circle and sample here, the X-ray beam hitting the sample, and you detect the fluorescence using the wavelength dispersive system with an analyzer crystal, focusing at the same time the signal to the detector. You are able to get a better resolution. Initially, this system would have been very interesting for radioactive materials in the sense that you are removing the radioactive signal, not saturating the detector, because you have an indirect detection system. So you can, at the same time, choose the emission line you are interested in and remove the background coming from the radioactive decay of your sample. And here you have an example of one of these spectrometers as installed in the Mars beamline at the Soleil synchrotron in Paris, or near Paris, where you have the beam coming from here, hitting the sample installed here, and then the fluorescence is diffracted by these 4 crystal analyzer, so bent, spherically bent silicon and germanium monocrystals, and focusing the signal on the detector here. When you do that, actually you are not anymore in the X-ray absorption regime, or the proper X-ray absorption regime. You are somehow in the photon in, photon out, two-photon phenomenon, where you are at the edge of between X-ray absorption and X-ray emission, which is related to resonant inelastic X-ray scattering, and it is called HERFD-XAS, where typically you have a virtually reduced cohort broadening, which has been demonstrated firstly by Hämäläinen in 1991. So typically what you collect is a part of the Riggs map, where you have the excitation energy here and the final state energy, so the fluorescence energy as a function of the excitation energy. You have a signal like here. If you're in a standard X-ray absorption measurement, you are integrating all over this line, but because you have the possibility to have a very high resolution in the measurement of the emission line, actually the HERFD-XAS correspond to a cut, a slice along this diagonal here. And because of that, you are virtually reducing the core broadening because you are taking into account not the initial state, but the intermediate state, meaning the final state of the X-ray absorption, which is the initial state of the X-ray emission. And usually the initial state of the X-ray emission is a higher shell, which has a lower core broadening. And here you have an example on one of uranium compounds, where you have comparison between the transmission in black dots, the total fluorescence yield in red, and the high resolution in blue, where you can see features more resolved, and comparison with calculations made using HERFD-XAS, where you can see all the features and can try to explain all of these features as well out of it. Yes, so it's time for a little bit of questions. So you know why we are studying these materials and what to use in order to get the best information out of the samples.
Okay, thanks. Any questions from the audience?
Hi, Toshi.
Yeah, go ahead.
Hi, René. A good talk, interesting. So the increase in resolution with HERFD is obviously quite useful and significant, but it's a long way away from where FDM and ES is maybe correct or maybe approaching. So maybe that's in the second half of your talk, of course, but I just wanted to say both of those are really interesting and complex issues to look at.
Yeah, thanks. And usually the calculations, especially FDMS, because it's DFT based, normally nobody has to use DFT in order to understand X-ray absorption, because DFT is essentially the ground state calculations, right? And we are not in the ground state anymore when you perform X-ray absorption. But luckily, it works quite well most of the time.
Good. Any other questions or comments?
So can I ask?
Yeah, sure.
I'm Kiyotaka Sakura. So thank you very much for your nice talk. So I'd like to ask you about the experimental setup. So you use SDD, but usually the HERFD-XAS people use the imaging detector.
Yes, it's essentially because you need something which is very small in order to be able to get very close to the sample in this geometry. Because you have to choose the Bragg angle according to the Bragg law, and the best resolution is achieved when you are near the backscattering, and that means that the detector is getting very close to the sample itself. And if you use a germanium detector, you get a very nice energy resolution with the germanium, of course, compared to SDD somehow. But because you have the wavelength dispersive, you don't need the improvement. But you need to have something very compact in order to be sure you can probe all the Bragg angle, which are the best.
Okay, thank you very much. So you use the sealed detector. What does it mean? It is special detector, special SDD? Sealed?
No, it's not so special. This one is just a detector. It's just the state-of-the-art detectors. Typically, the one who have a resolution at the KL of manganese of 140 EV, something like that.
Yeah, something like that. Yeah. So not so special, but it's usual, normal SDD. Sorry, silicon drift.
Yeah, exactly.
Okay. Mm-hmm.
It's
Thank you very much. Okay, thank you very much.
welcome.
Okay, any other questions? Okay, is it hard to set up this crystal to get focused on the detector, or is it easy? I mean, how long does it take to get a good resolution?
You mean
To set up
good resolution? To setting up, it's not taking much. Well, it depends on the beamline and how much crystal you have, but typically it's a matter of a few hours at maximum if you have to realign everything from scratch. Most of the time, when you have aligned it once, it should be okay for. You just have to check that the new sample is at the focal point here, and that's it.
Okay, so not so wrong.
Yeah, the issue comes from the fluorescence yield, of course, and the solid angle you are covering with your crystals. So the more crystals you have, the better, because you are covering more and more solid angle. And of course, as I mentioned with HERFD-XAS, you have to select one emission line, and the emission lines which correspond to, which may have the best resolution improvement, are usually the one which have the less fluorescence yield, because they are you have to get initial state for the fluorescence to be the highest as possible in terms of orbitals, and so it's the most difficult one. Usually you get better resolution at the expense of the counting time.
Okay, thanks. Okay, so we will enjoy the second half talk.
Yeah. So let's go to the details with the case of KU3. And well, all what I will show next will have been made at the SRF. Uranium L1H and L3H has been measured at the BM20 beamline using a silicon 111 monochromator, and an X-ray emission spectrometer equipped with 5 silicon 220 analyzer with a bending radius of 500 millimeters. And you can have more details on this device apparatus following this paper. For the M4H, this has been made on the ID26 beamline, using also a silicon 111 monochromator, and then similarly 5 silicon 220 analyzer, but this time a bending radius of 1 meter, which is improving the resolution because reducing the Johann approximation in terms of the emission spectrometer. And the calculations I will show has been made using the FDMNS code. For this particular case, we saw no difference between using the finished difference methods or the multiscattering approach. Multiscattering approach being less expensive, theoretically wise and calculations wise, we focus on multiscattering approach. So the one which is also used in the FEF code, for example. And we use KU3 clusters of 9 angstrom radius, taking into account the spin-orbit coupling and relativistic effect because it's uranium, self-consistent field, and we look at the dipolar and quadrupolar transition probability because it has been demonstrated thanks to the high resolution lately that at the uranium L3H there is a quadrupolar transition which is overlapping with the these states as probed during the L3H zones. Okay, let's start with one of the edge usually nobody wants to see, essentially because of the resolution, which is very bad because of the cohort broadening. And we were able to reduce the resolution down to 12.5 instead of more than 17 EV by collecting the L bit of 4 emission line, which was, instead of having the 2s cohort broadening, we got the 3p half cohort broadening. And here you have the experiment in black dot, where we can already see, thanks to the improvement in the resolution, different spectral features, 2 shoulders on the white line, S1 and S2 here, and 2 features after the white line, A and B. And in order to understand what we were looking at, we made the calculations. And here you have a comparison of the density of states of the p states, because we are probing the p states in that case of uranium. And you can see that there is a very nice agreement between the calculations and the spectral feature we can see on the experiment. Some of the features seems to be closer, well, shifted in energy compared to the experiment, and this may be the impact of the DFT calculations or something else which is affecting this positioning. In order to get better insight into these calculations and understand more where those features are coming from, we compare the density of states of each element separated in orbitals, so uranium P, uranium D, uranium F, and also the ligand, oxygen P and potassium D states. And we compare to see where these peaks are coming from. And if you look at A and B, typically you have almost an overlap between oxygen P features and uranium P features, meaning that there is probably a link between the uranium and oxygen bonding with this position and these features A and B. Concerning the S2 shoulder, the first, so the white line, which is a little bit broadened, you have 2 groups of P states here, which are separated. And this is not well understood yet because this could be linked to the fact that there is crystal field splitting of the P states, which is unexpected. But we have to dig further in the sense that there could be also an hybridization between the D states, which are splitted, as you will see later, and the P states. So meaning that we have 2 bands here of P states, making a broadening of the P states of uranium. And then there is the S1, which was also unexpected. So we thought at the beginning that it could be a kind of quadrupolar transition, because you have a huge amount of D states of uranium in this positioning. But this is really unlikely, in the sense that the intensity is way higher, and we are in a very symmetric configuration of ligand around uranium. So the intensity of this feature should be very low if it exists. So the other possibility was hybridization of uranium 5F with oxygen 2p, making the 5F having a 2p p character, and then allowing the transition in this small shoulder. So that means that maybe if it's the case, we will have a feature here which should be very sensitive to oxidation states as well. But well, this is just hypothesis, and it needs to be dig further, especially because not so much is known about the L1H of uranium so far. But one which is well known is uranium L3H, and we were able to go the resolution down to 3.9 essentially on the measurement. And here you have the L3H measurement of these compounds in black dots, along with the calculations we performed. You can see as well a very good agreement in the sense that you have two groups of D states in the white line, then a few features A star, B, and C, which are slightly shifted in energy in the calculations compared to the experiment, but still a very good agreement. As expected, the D states are split in T2G and EG groups, and because of the octahedral crystal field, and actually because of the resolution improvement, we were able to measure directly the field strengths because it's directly proportional to the peak separation. And because we are able to distinguish the two peaks, we were able to measure the 10 dq, which was found to be about 6.6 eV experimentally, with a huge uncertainty, of course, because the two peaks are not well resolved, well, enough resolved to have a better formation. And from the calculations point of view, we obtain a value which is very similar, about 6.9 electron volt. We use the same way of looking deeper on the features and where they are coming from by looking at the F states and as well the D states separated in two groups, the one responsible of the T2G and the one responsible of the EG. And we saw that, for instance, the A and A star peaks are mainly related to T2G like d orbitals of uranium appearing after the crystal field splitting. So it's still the crystal field splitting having an effect at higher energies. And even B and C features are linked to the same orbitals from EG, with C being already a mixture between all the D electrons. In addition, if you compare to the oxygen density of states, you can see that A and A star are linked to essentially to oxygen PY and PZ orbitals. So there is a link between uranium and oxygen in those orbitals. While for B, it is essentially oxygen PX and essentially oxygen PY, PZ for the C electrons. So there should be sensitivity to geometrical distortion or in these features, and it would be interesting to see what such distortion affect the positioning of B and C and A star as well, for example. And the last edge we were measuring is the uranium M4 edge. Here you have the overall edge with a very sharp white line, where because we were able to reach 0.5 electron volt resolution by measuring the N beta emission line. So having the broadening coming essentially from the 4F electrons. This white line here, zoom in, is very sharp, but so it will be very highly sensitive to uranium oxidation state, but it is still slightly broadened. As you can see, there is a kind of a shoulder on the right side, so the high energy side, which is probably the consequence of the crystal field splitting, and I will go back to it later. And in addition to this, there is several post-edge features, so they are a little bit harder to see in this slide, but I will zoom in afterward because of the very huge white line. And those post-edge features, if you zoom in here, and you compare them to the calculations, you can see a very nice agreement as well, a slight shift of some of the features again. And you can get more details by comparing the uranium F electrons, because we are probing the F electrons directly, and comparing the different orbitals you may think of for uranium F. And we can see out of it, but some of the features are directly linked to only some of the F orbitals, while some others, like the E features, the smallest one here, is a mixture of two types of orbitals. And if you compare as well on the same way using comparing with oxygen, you may have insight of which of these features are linked to bonding or anti-bonding with oxygen p states as well. So lots of these features may show sensitivity to any change in the uranium-oxygen bonding and the ligand geometry as well. So by comparing these features between different compounds having different geometry around uranium, we may get even better insight of the bonding itself between uranium and oxygen. Yes, so I show mainly the results we obtain on different edges, and it's probably time for a few questions.
Okay, thanks. Okay, so any questions from the audience?
So can I ask?
Sure.
One question is, you show the hybridization between uranium and oxygen, right? So the oxygen P X P Y P Z. So X Y Z, what does it mean?
It's
Bonding direction or?
It's the cubic harmonics of orbitals. So it's just a traditional way of making the orbitals in 3D space. But you can imagine other type of distribution. It was just the easiest way, which is allowed by the HERFD-XAS code, actually.
So X is fixed to the crystal axis, or X is defined as the bonding direction?
X depends on the crystal axis.
Crystal axis.
So in KU3, X will be along. If I go back.
Yeah.
If I go back here, so X will be along some of the Woos oxygen in this line. Y would be in this direction. YZ would be in vertical line.
That direction.
So typically for the oxygen, there is a kind of alignment which is expected if you consider those octahedra in X, Y, and Z. But then if you consider the other orbitals, which are more complex, like the D and F, you may have the orbitals pointing somehow in the diagonal, or and meaning that there should be less interaction or bonding between oxygen and uranium using these orbitals, if they are not well aligned with this.
So therefore, the oxygen to P is split by the directions.
Should be, yes. So it's the most important. In that case, it's almost the perfect case in the sense that they are well aligned in the right direction.
Okay, thank you very much. Okay.
Okay, questions from Aurolovetsik? You will talk by yourself, or?
Yeah, I can state myself. Yeah, thanks for the presentation. I was wondering, I see, actually in this, for example, there is always a shift. So for example, the peak D, E, and F. So the final structure, you see a shift there with respect to simulation. So this led me think that there is something wrong in the lattice parameters, right? Because this is the final structure. Can you comment on this?
There is two things. The lattice parameter I used for these calculations was based on the one we deduced from HERFD-XAS on the same compounds, which was found to be a little bit higher than the XRD we made as well. And if you I made also the calculations using this HERFD-based lattice parameter, and the peaks were slightly moved to higher energies, slightly.
Okay.
The thing is that even when you know the right lattice parameters, well, if as much as you can know it perfectly, I found out that on uranium calculations using HERFD-XAS, there was always non-linear shift behavior in the high energy side.
Okay,
On many
yeah.
uranium
So, yeah,
compounds I
okay.
calculated. So maybe
Okay,
it's
so
related, I suppose, to DFT effects or something.
Okay, yeah, I see. Yes, so I understand. So if I understand correctly, your answer is you have tried different lattice parameters and the shift. I mean, you don't observe a linear the shift as expected. Yeah, you don't. The shift doesn't go well. Doesn't go well with the lattice parameters.
It's
Yeah.
improved. It improves a little bit the higher energy side.
Yeah.
But then it degrades a little bit the position of the low energy side. So it has a non-linear effect depending on where you are situated compared to the white line.
Okay, yeah, I understand. Thanks.
And one track I followed was as well the HERFD-XAS by default is calculating the electronic configuration being neutral. And maybe some improvement can be made by not taking uranium as neutral, but getting closer to its 5+ configuration. It has shown in the past very nice improvement for MH at over actinides. I mean, plutonium and americium, for example, we were able to reproduce very well all of these features just by transferring some part of the electrons from the actinides to the oxygen. And this has solved the problem. But it's essentially a trial and error solution. And it's better to have a more solid framework in order to do it properly.
Yes, thank you.
Questions from Chris first and then Peter.
Thanks. Also a good talk. I think one of the best things that come out of this, from my perspective, is the potential for using HERFD in general to look at particular edges and see different sets of structure that, of course, then are a big challenge to understand theoretically. And I think that's one of the really nice things that comes out of your talk. Thanks very much.
Yeah, thank you. That's true. It's a good opportunity to have lots of positioning in energy of many features because of the improvement in energy resolution. And then it's a good opportunity to compare with calculations and understand better if the calculations are failing or are giving very nice results and how to improve them.
Okay, Peter.
Hi. I'd like to make a comment about question one before about the peak positions. In my experience, I think it's quite normal that you can have upshift. I mean, that the experimental peaks are higher than the theoretical peaks in higher energy because, and the reason would be that the exchange correlation potential that is used here for a ground state calculation is not so well adapted for higher energy states, and you have kind of optical potential effects. I think this is rather common. And if you look at the peak positions here, you have some which are very good at the low energy part, and then it gets worse. I think this is quite, or there might be many reasons, as you said, also about the charge and so on, but I think this is rather common and not too much to worry about for the lattice parameter in my experience.
Yeah, it's what I observed many times by calculating different compounds. HERFD-XAS was demonstrating very nice peak positioning closer to the white line, and then when you get at higher energies, it was drifting. And even on the low energy side, I mean, for the field orbitals, it was the same a little bit. Just shift which were not linearly. So like we were very good to the white line, and then we are getting away on both sides.
Right. Somehow, as long as you're below the +1 peaks and so on, the ground state exchange correlation potential is doing quite well. But then above, you need somehow another exchange correlation potential, which you can put in some codes, so maybe not in FDMNS. I don't know. And then I have another question about, again, to what Professor Asakura already asked about this p-dose. It's also not clear to me. If you look at the symmetry of your potassium uranium oxide, this is totally cubic, isn't it? So then shouldn't be all the three dose pxyz be the same? And even if you project on one oxygen that is maybe on an axis between two uranium atoms, you should still have at least two others, say Y and Z, to be the same. So for me, this is not clear why this comes out so differently. Well, maybe it's a detail.
Let me think. Normally it's perfectly cubic, so they should be almost similar. But I think it comes from the way the harmonics are made by themselves, showing a slight difference, because the Py and Pz are probably a mixture of the P states. I have to, well, I cannot figure out by heart right now, but I can have a look later if you want.
Thank you. Yeah. That's all.
Yes, thank you. Many good discussions. And any other questions or comments? Okay, I have a question. You measured uranium L1, L3, and M4 edges.
Yes.
And what do you think about which is the best edges to understand uranium electron state, or do you need all three edges to understand totally the electron structure of uranium, or do you have any comments on it?
Well, if you want to very well understand the electronic structure, you need all three, and in the perfect world, you would need also to have something able to measure the S state as well, so to have a complete overview. Nevertheless, most of the time, F states and D states are the most common. So L3 and M4H would be the must have in the sense that they will be the most prominent in what is happening nearby the Fermi level in the bonding. The P states measured by measuring L1 would be a kind of a bonus and will give you more insight, but they should be secondary. And the problem with the resolution, which is still not as very good, is still a problem. So M4 and L3 would be quite the must-have, I would say.
Okay, thanks. Any other questions? Maybe Peter already asked his question, so. Okay, if not, René, do you continue and summarize your talk, or?
Yes, there was the last part, which is quite short, so it would be easy. Because of the calculations, we were quite in good agreement. We decided why not going beyond X-ray absorption using what we call XAS calculations, because there was good agreement between calculations and three different edges. And we were able to look at the crystal field splitting of uranium 5F, which are responsible for the white line broadening on the image. So if you look at the theory, there should be the 5F1 at the free ion. Then you put the octahedral crystal field, which is split it in three states, and then the speed orbit coupling, which you will divide it then more in different states. And we look at what the calculations gave us. And well, there was plenty of peaks, and the most intense one were attributed to what we were expecting from the crystal field splitting in the octahedra. And we compare them with literature where we found some forbidden Laporte FF transition determined experimentally on this compound. And here you have the example of the line we found with the position in milli-electron volt as a function of two studies we found in literature, both experimentally and calculated. And the agreement was not so bad in the sense that, well, there is plenty of lines, so it's not very difficult, but still we were able to compare both experimentally and the experiment and the calculations made in the past with our own calculations, showing that there is probably more to dig in this crystal field splitting of 5F electrons, maybe using more adapted code or making a new measurement of the forbidden Laporte FF transition. In that case, in these compounds, with better resolution, we can achieve nowadays, for example. Another application would have been, let's have a look to the electron binding energies just right below the Fermi level. And so the idea was to compare directly with XPS and X-ray emission spectroscopy data. But for potassium uranate, there was only data for the uranium 4F, which is used in XPS essentially for determining the oxygen state of uranium. But there was two studies which were in good agreement experimentally, and with our values, they were not very good agreement, but it's essentially due to the fact that our values in energy have a different energy scale. We are giving the energy from the Fermi level, while the XPS measurements are given compared to one line of carbon usually, which used as the reference in energy. And there is also a lack of experimental data because we were able to have the calculations down to this energy, so down to the 4F, but we have all the positions of the binding energies in potassium uranate for the other shells to 0 electron volt, typically. And a little bit to tease you, what's next? Actually, we wanted to have even better resolution at LFEH, and this would be possible by using another monochromator, silicon 311, and going to the L beta 5, so having the cohort broadening of the 5D electrons. So in the past, it has been showed by Krishna Vashnina that it's possible to achieve a resolution on the order of 2.4 electron volts at uranium LFEH, which showed here on uranium dioxide. She was able to show the splitting of the white line of the D electrons in uranium dioxide, which is very, very small crystal field splitting because it's cubic around oxygen. And so the idea was to get this resolution, and it's what we had last month, actually, well, a few weeks ago, where we were able to measure on the potassium, sodium, and rubidium uranate at the SRF as well, achieving the same type of resolution. And here you have the preliminary results where we compared for all three compounds, the L-alpha-1 and L-beta-5 HERFD-XAS. And you can see that we are now able to have the two peaks due to the crystal field splitting. So we have an even better evaluation of this and the ability to compare the spectrum of all of these compounds and see what is the effect of distortion of the octahedra and even elongation of the bond lengths. So it's work in progress, and well, we will have it out soon, hopefully. So to conclude, HERFD-XAS is really a powerful tool to probe the electronic structure of uranium because of the improved energy resolution. So you can directly measure the crystal field splitting if you have the right enough resolution. And you can show directly experimentally hybridization of uranium and oxygen ligand, because some features are directly linked to this. And that will lead us to a better understanding of the degree of covalency in uranium bonding and a better understanding of the electronic structure of uranium. The problem is that to understand this new data, it requires accurate calculations for the interpretation. And so maybe we are getting towards the limits of the actual codes, and we need to get to more complex theory behind in order to reproduce all the features which are visible. And that's all for my presentation of today. So if you have more questions, I'm happy to answer.
Okay, thank you for a very nice talk. Now he accepts more questions, comments from the audience. Any questions and comments? Okay, so the last slide, the better resolution at L3H. So it means we can discuss directly comparing the white line peak and crystal field splitting, right? Yes, normally the difference on the position of these two peaks is directly the 10 dq of the crystal field splitting of the d electrons. Okay. But there is something in addition, because the L3H, thanks to the HERFD-XAS, it has been demonstrated that there is the quadrupolar transition to the 5f electrons, which is typically as a shoulder on the white line, and because of the splitting, typically some of the 6d electrons are pushed back down in energy, so there is a slight overlap. So it would be correct to have this distance in energy as the crystal field splitting, but we have to keep in mind that there should be also the f electrons movement, which may affect the peak, the first peak position or intensity somehow. So it's a little bit more tricky, but if you have also the NH measurement, so directly measuring the 5f electrons, you can separate both of them in the sense that you will have the information on the change in the 5f, which are probed in the quadrupolar transition here, and keeping the dipolar pure somehow. Okay, thanks. Any other questions?
So, can I ask?
Sure,
so,
sure.
According to this picture, so you showed, to my eyes, the sodium case, peaks, two peaks, splitted peaks are sharp.
Yes,
or they were separated. Or separation of the two peaks are the same for the rubidium, sodium, and potassium?
Not exactly. There is some changes, which is in good agreement with if you compare rubidium and potassium, there is some changes in the peak position because the crystal field in rubidium is less important in the sense that you are pushing the oxygen a little bit at longer distance, so it will be less effective, which is making sense. And for the sodium, well, the distortion in the octahedra is affecting the position of the peaks, and even these two peaks here, two features you have here and there, you have almost only one, only, which is in the middle for the sodium, which is due to the distortion in the octahedra, and even the tilting may have an impact on it.
So what I think is the sodium is highly distorted, therefore to me, it is natural that the broadening occurs in the sodium case, but the experimental result is different. So the sodium is a little sharper, even if it is so distorted. Rubidium and potassium are, on the other hand, broader, even if they are the octahedral, nearly perfect octahedral. So that is curious for me. Yeah.
That's really counterintuitive, and that's why we are still digging in it, because there should be some other effects in the positioning of the d electrons in that case.
Thank you very much. Yeah, very interesting.
According to his question, I think sodium is tilted, I mean, counted. So the cluster, I mean, the minimum complex is something like more, I mean, independent from the other clusters. So I think it's natural the sodium is sharper, because the interaction between other, I mean, clusters is weaker than the other rubidium and potassium case, right?
Because of the tilting, yes, probably. And there was some theoretical work in the few years ago about some electron transfer, which should be more important if you have an octahedra along a line, or if they are tilted to each other, then the electron transfer will be less, and therefore this may have this impact here. Well, it was a theoretical work for the 4F electrons, but one may expect almost, well, probably a similar behavior for the 5F somehow. Okay. But yeah, it's a little bit counterintuitive, because well, we did not expect to have as sharper separation for sodium uranate.
Okay. Any questions from the audience? More? If not, okay, thank you, Dr. Lunes. Thank you for a very nice and beautiful results and talk.
Thank you for the invitation. It was a pleasure.